what I would like to talk about today is a little bit more about continuous functions, and then time permitting, we'll go on to something a little different. I would like to talk about the extreme value theorem. This is one of the classical theorems from calculus. The extreme value theorem. It has to do with the minimum and maximum values of a function, right? Something that, you know, the way that we say this in calculus is if f of x is continuous on a closed interval, say a to b, then f of x has a minimum and a maximum value. In calculus, we usually refer to this as an absolute minimum and maximum on the interval a to b, right? And those values, they either occur sort of at a relative maximum or minimum, or they occur on the endpoints. Does this sound familiar to anybody? The absolute maximum and minimum, they occur at a point where the derivative is 0, or they occur on the endpoint of the interval, right? Those are like the mountain peaks or just the ends. Well, here's a fun fact related to the extreme value theorem. You can quiz your friends about this one. This is a fun fact. Bring it out at parties. I learned this a few years ago when I went hiking with my kids. We went to the highest mountain peak in the state of Connecticut. It's not very high, but it's in like sort of near the border of Massachusetts and New York, like in the northwest part of the state. The highest mountain peak in the state of Connecticut. I later learned, doing some research, that the point that we were at, the highest mountain peak in the state of Connecticut, this is a true fact. The highest mountain peak in the state of Connecticut is not the highest point in the state of Connecticut. What do you think of that? You can ask your friends at the club. How is it true? How is it possible? And I'm not, this is no funny business here. I'm not talking about like there's some like very tall tower or a big tree or something like that. No, the answer is completely ordinary.
It's at the end of the interval.
Yeah, it's at, the thing is the highest point in the state of Connecticut is not at a mountain peak, it's on the edge of the interval. This is the thing from the extreme value theorem. You know, a function, it can look like this, right? And this is a true fact. The way it really is in the state of Connecticut is something like, not like that, sorry. I meant something like this.
I know that fact, and I can't figure out how I know it. Somebody told me. Bernard told us that? Okay.
Oh, really? Okay. I didn't know that he knew this fact. That's interesting. Anyway, like this is the state of Connecticut, and then this is the border with the state of New York. The highest mountain peak is like here. But actually the highest point in the state is on the end, right? That's how it's possible. It's because the extreme value theorem doesn't tell you that the highest, so I'm talking about the absolute maximum, right? But the theorem doesn't tell you the highest point occurs inside the interval. It might occur on the edge of the interval, which in the real world means it's not on the mountain peak. All right, excellent. I had a long discussion once with a guy in China. I went to China to a math conference. And on one day, there was like an excursion day, and we all went to the Great Wall. And this is like a part of the Great Wall, which is near the city of Beijing, and where the wall like goes over these mountain ridges. And I asked our tour guide, are we right now close to the highest point on the Great Wall? Because we were like in the mountains. I thought maybe this is like the highest point. And he was like, no, like, what are you talking about, highest point? I said, well, you know, like, I don't know, like the highest point. He said, no. There's some points are higher, some points are lower, but there's no highest point.
Doesn't there have to be?
Yeah, in my opinion, I think there is a highest point somewhere because the wall itself is it's kind of like a closed interval. I mean, it's not like it goes on forever, so you could say, oh, there's no highest point because it like goes up to infinity. No, it doesn't do that. I was never able to convince him that, that there really is a highest point of the Great Wall.
There's a language thing. Maybe he didn't understand what
Yeah, he was kind of like disgruntled with our group, and especially me and some other Americans, because I think he had the idea that like we were sort of idiots when it came to the Great Wall, which is fine. Like I'm prepared to be regarded as an idiot when I'm abroad identifying as an American. Like I'm cool with that to some extent. But the other question I had for him, this is maybe like a distinctly American question. I asked him, is it like a thing, how common is it for people to walk the entire distance of the Great Wall? And he was like, that's ridiculous. Nobody can do that.
Yeah, wait, trail.
And I said, like, well, I mean, he said it's way too long for that. And I said, like, yeah, I know it's really long, but you know, like I'm thinking of the Appalachian Trail. Like there are really long things in the U.S. that people do the whole thing. He said, no, it's way too long. Like where would you even sleep? I was like, okay, he doesn't really understand what I'm saying, but yeah, he said like, how would you get food? I said like, well, I don't know, you have your friends drop it off or something. I don't know, you know.
What
Like,
they should do, they should turn that into a thing where they have little, like they do on the trails, where they have, you know,
yeah,
little things for you to set up camp.
right. I mean, so I did some research later and learned that yes, people have done this, but it's not really a thing. Like, I think maybe this is like a distinctly American idea that like, when I see a big thing, I want to like do that whole thing, right? I don't want to do it myself, but like it occurs to me, well, somebody must do the whole thing. And apparently this is just not the way that Chinese people think about it. Also, like the Great Wall is not just a long thing. It's more like this. Like it has many different sections, and they don't even all connect to each other. So it's not even really, you can't really say, oh, I'm going to walk the whole thing. Like, I mean, you could, I suppose, try and cover the whole thing, but it's not so simple. Anyway, I still fondly remember the tour guide at the Great Wall.
I'm sure he remembers you and your group as the American idiots.
Yeah, I don't know. He probably talks to American idiots all the time. It's probably like the same. Maybe he's probably met actual American idiots. Maybe I'm an actual idiot. I don't know. Yeah. Okay. Anyway, the extreme value theorem, right? I want to talk about this. It turns out, so I'll just scroll up. I don't need to write it again. I would like to talk specifically about this right here. I would like to ask the particular question, does it need to be a closed interval? All right. Is the same statement true if you use instead an open interval? Actually, the answer is no, it's not true if you use an open interval, because if you omit the endpoints, then it's possible that the function, it sort of increases up to the endpoint but never actually arrives there, so it doesn't have a maximum. So it doesn't work with an open interval, but what about any closed set? Does it have to be an interval, or could it be some other closed set? All right, this is the kind of question that I would like to ask about. Let me just say there's another way of writing this statement. So equivalently, we wouldn't typically write it this way in a calculus class, but it is another way of writing the same statement. If, well, let me just say that, yeah, if f is continuous, then this set f of the interval AB, the closed interval AB, is a closed interval. This is a true fact. You can see, for example, if I have, I'm just going to draw an example here, f of x equal x squared, say. Looks like this, everybody knows. Just to refresh our memory, what do I mean by f of the interval? This is something we usually don't talk about in calculus because usually you don't want to teach calculus students what the set theory behind this. But what f, I'm plugging a whole set inside the function f. What that means is I'm considering the set of all values that come out of the function when you're plugging in things in the closed interval a to b. Like, for example, if I used here, say, f of specifically -2 to 4, what would that be as a set? It means you look on the graph here, and you go back to -2, and you go over to 4 here. That's the interval, in the domain. And then what is the corresponding set in the range that you get from plugging those values in? Can anybody say? What is the set of y values that you get out when you use those x values? Yeah. Yeah, 0 to 16. So this can be a little tricky. I mean, it's not so difficult in this case. From here up to here, right? 0 to 16. If the function was weirder, it's not guaranteed to be easy at all to figure out what that is. You don't, for instance, you don't simply plug the two endpoints into the function. Because you can see that's not how you would do this one, right? You would get 4 to 16, which is not right for this one. You have to understand something about how the function works. But anyway, if f is continuous, then f of a closed interval is a closed interval. If you think about it, this means there must be a minimum and a maximum. What are the minimum and the maximum? They are these two numbers, right? This is the absolute maximum, and this is the absolute minimum, right? So to say that there is an absolute maximum and an absolute minimum is, at least, it's not exactly the same, but it's related to the statement that when you plug a closed interval into a continuous function, the answer is also a closed interval. Not only do you get the maximum and the minimum, but you get all the values in between. And that's sort of related to the intermediate value theorem, which is another thing from calculus. You get all the ones in between also. All right. Anyway, again, I want to answer the question, is it necessarily closed intervals here? Or could it be something a little more complicated? For example, well, forget it. I was going to say, for example, the Great Wall of China is not exactly an interval, but is enough like an interval that it should, I feel like it should have an absolute maximum and absolute minimum when in that case, the function you're talking about is just like the elevation or the height of any point along the Great Wall. It's not exactly an interval, but even something that's like an interval, but maybe in a few separated pieces, it ought to still have a maximum height or whatever, right? Okay, I'm going to live the rest of my life trying to prove that guy wrong. I did look it up, actually. There is a highest point of the Great Wall, and it was not where we were. So I found out the answer to that question. Anyway, I'm here to tell you this fact is true, and this is what I want to talk about. This fact is true for, it's actually not true for any closed set, but it is true for any compact set. Compact, remember, means closed and bounded, or that's the theorem. The Heine-Borel theorem says a compact set is closed and bounded. The definition was that, does anybody remember the definition? I know it's been a while since we talked about compact sets. Eventually you'll want to remember this for our next test. It has to do with sequences. You remember? Folks back home want to shout it out? I don't know if my sound is, I don't know if they can talk to me. I hope they can hear me. Anyone remember? Compact means that if you have a sequence in the set, then it has a convergent subsequence which converges to a limit which is also in the set. All right. But anyway, this fact is true for any compact set. So I'm going to try and prove this as a theorem. The proof actually is not really difficult at all, provided that you remember the definition of compact. So it says if K is compact and F is continuous, then F of K is compact. So remember before I said if it's a closed interval, then F of the closed interval is another closed interval. That is more generally true for any compact set. F of a compact set is compact, if it's continuous, all right? This actually is something that, as I was standing there arguing with the tour guide at the Great Wall of China, my friend, I was with like a bunch of mathematicians, and they were all sort of, laughing amongst themselves because They knew exactly what I was trying to explain to this guy, and the guy was clearly not understanding what I was saying. And my friend Yurik from Poland said, no, Chris, you don't understand. The grid wall is not a compact set. He was referring to this theorem. I was trying to sort of reference the extreme value theorem. My friend from Poland was thinking of the general version, which involves compact sets rather than closed intervals. The gray wall is a compact set. Okay, let's see if we can do this. If K is compact and F is continuous, then F of K is compact. Maybe before we start, can I just refresh your memory? K is compact. I said this out loud, but I might as well write it down. This means that any sequence xn in K, if you have a sequence of points, it doesn't mean that it converges, but it has a convergent subsequence. I'll write it as x sub n sub k. Remember, sometimes we write subsequences as like this sort of double subscript. It has a convergent subsequence, and the thing that that subsequence converges to is also part of K. That's what compact means. All right. So we let's prove the theorem. We assume that K is compact, so let K be compact, and we need to show that F of K is compact. So I want to show F of K is compact. What does that mean to show something's compact? You take any sequence in F of K, and you have to show that it has a convergent subsequence. So I'm going to say take, now I'm going to call them Yn in F of K. I call it Y because I imagine that these are like the Y values of some function, right? F of K refers to all the values that you get out of the function when you plug K in as the domain. So that's why I call them Y. You can call them X if you want to. So I take Yns in F of K, and then I'll say we will find a subsequence which converges to an element of F of K, right? And if we do that, that means that it's compact, because that's what. So compact means any sequence has a subsequence that converges inside the set. All right. What do we do? Since all we have to work with is that Yn is in F of K, what that means is if every one of those Yns, it is equal to F of something from a point in K, right? So each Yn, I will say, comes from some xn in K with F of xn equals Yn, right? The Yns are all in F of K. That means each of them is the answer that you get out of the function of some number that you put in. And the xn's are in K, all right? So we have a sequence xn, which is in K, right? They are the domain values which end up going on to those points, the Yns. Since K is compact, anybody see where I'm going with this? What can we say about this since K is compact? We have a sequence xn that's in K. So what can you say about that since K is compact? Yeah. Kind of. He said xn converges. That's not exactly true, but a compact set doesn't mean that the sequence converges. See up here.
Xn converges set x and
So it means that this sequence has a convergent subsequence. It doesn't necessarily converge, but it has a subsequence that converges. So I can say since K is compact, there exists a subsequence X and K converging to X, where X is some point of K. All right. Really what we are looking for is a subsequence in F of K. That was our original thing, right? Is that we will find a subsequence which converges to an element of F of K. But here, you can just, like throughout this whole thing, apply F to everything. What does that say then? It says F of X and K converges to F of X. And why can you do F there? It's because F is continuous that it still converges to what you want it to converge to. All right? That's because of the sequential version of continuity says if something converges, if X ends converge to C, then if F is continuous, then F of X ends converge to F of C. That's what we're using here. So I'm going to say this since F is continuous. All right, but this F of X and K is equal to Y and K, right? That's what I called F, like up here, right? F of Xn is always equal to Yn. And so when I see F of X and K, that's the same as Y and K. And here we have a subsequence of the Yns, which converges, right? And in fact, F of X is going to be an element of F of K. Should have written that in there. Because the X was in K, so the F of X is in F of K, all right? So Y and K converges to an element of F of K, and that's it, right? This is what we wanted, right? We wanted to show that there was a subsequence which converges to an element of Fk, and that's what it is. All right? So the moral of the story is this extreme value theorem, it actually holds for compact sets. Now, we didn't actually say that this f of k has a minimum and a maximum. We just said that it's compact. But that automatically means that it has a minimum and a maximum. Let's just try and explain that. So this is the connection to minimum and maximum, right? The fact that f of k, does f of k have a minimum and a maximum? That's really the question. Right? It does. The answer is yes, but we should explain why. Why is that? What does that have to do with compactness? Actually, compactness is how you demonstrate that it has a minimum and a maximum. So f of k is compact. And remember the Heine-Borel theorem. That means f of k is closed and bounded, right? A closed and bounded set. Now, bounded means, first of all, that the sup exists. The sup is the least upper bound. So I'll say bounded implies that the sup exists. Now, the sup is different from a maximum because, like even if you have like an open interval, the sup exists, but it's not a maximum because it's not part of the open interval. So we additionally would like to explain why is it part of the set. But that's because it's closed. So closed means that the sup is actually an element. That's because the sup of a set is automatically a limit point, right? And therefore, if it's a closed set, then it contains all the limit points. And so that is an element. This is because the sup will be a limit point. That's actually not always true. It's true as long as the sup is not an isolated point. If the sup is an isolated point, though, then it's already the maximum point. I don't want to get into the details of that, but this is the idea. A compact set is bounded, which means the sup exists. It's also closed, which means it actually contains the sup as part of the set. And then that means it really is the maximum element. The sup would be the largest possible element that could possibly be in the set, and then it really is in the set. So the sup, this is generally true of any compact set. The sup of a compact set is actually a maximum element. All right, and then the same for if you want the minimum element, you just say everything I just said about the inf, and everything works out the same way. All right, so I'll just say same with the inf and a minimum. All right, so this is the proper generalization of the extreme value theorem. It's not just a theorem about closed intervals, it's about really any compact set, for which, you know, every closed interval is a compact set, but there are other weird compact sets. For instance, the Cantor set, the continuous function on the Cantor set automatically has a maximum and a minimum value, which is a little strange. Or something which is basically like an interval but chopped up into a few pieces, like, for example, the Great Wall of China. All right, all these things are true in higher dimensions too. There's like an R2 version of this theorem, which would apply to something like the state of Connecticut, which is not anything like an interval really, but it's more like a two-dimensional thing, but it is still a compact set. So you can still do this. All right. Any questions about any of that? That's all I wanted to say about that extreme value theorem. It's one of the classic, you know, important theorems from calculus. Let's go on to the next section then. For some reason, this is in the same section in the book as the next thing we're talking about, although in my opinion, it has not much relation at all. So I would say this deserves its own section break in the book. Uniform continuity. This is kind of a big idea, and maybe this is an idea that we are going to talk about, which has really no parallel idea in calculus. Most of the things we talk about are just sort of fancier or more technical versions of concepts that you've already learned in calculus. This one, though, we never talk about it in the calculus class, and you'll see why, because in order to make sense of this, it actually requires the epsilon and delta business for limits. But it's a fact, you know, everybody talks about some functions are continuous, some functions are not continuous. This is a stronger thing called uniformly continuous. So certain functions that you know and love are continuous. Some of those are uniformly continuous. It's like even better than continuous. Like I said, you need the epsilons to be able to make sense of what this means. Let me just refresh our memory about what ordinary continuity means. So for, I'll just say, F is continuous. So when you talk about uniform continuity, it's always about continuous on a set. You don't talk about uniform and continuous at a particular point. It's always about on some set. So F is continuous on some subset, A, subset of R. Remember what this means? It means for every point in A, you have that epsilon delta thing. So one way you could write it is this way. For all C in A, and then I'm going to write the definition of continuity. For all epsilon greater than 0, there exists delta greater than 0 such that, etc. We all know this. X minus C less than delta implies f of x minus f of c less than epsilon. Right? This is the definition of continuity. Now, when you're trying to like contrast this with uniform, this is not uniform continuity, what I just wrote. This is sometimes called pointwise continuity, to emphasize the fact that all I'm doing is just writing the definition of continuity at each point, all right? And I have this for all C and A out front to indicate it is continuous at every point of A. Okay? In many of the examples that we've done, maybe even most of them, I'll just say many examples, this, I don't know if you ever noticed this, and it's not something that you would have noticed really, but the delta depends on the C. This is a true fact, which probably was never worth remarking on before, but it's true. For example, I want to try and convince us of this. For example, how about this function? F of x equals x squared, C equals 3, all right? When you do the proof that this is continuous at 3, the delta will depend on the 3, and we'll see why. So when we say this is continuous at 3 means, I'm not going to write the whole thing, but for all epsilon there exists delta. X minus 3 less than delta implies x squared minus 9 in this case less than epsilon, right? You use the f of x minus f of c will be x squared minus 9. And then if you were trying to write this proof out, you would do it in blue, like I always do. I've done it in blue so many times, I feel like now I have to do it in blue forever. You factor this, x plus 3, x minus 3. And the x minus 3, I like that the way it is. The x plus 3, I don't like that. Anybody remember the trick that we do for that? Yeah.
Delta is greater than or equal to 1, then x has to be greater than or equal to 4.
Yeah, right. So if delta is less than 1, then x needs to be within distance 1 of 3. Oops. There's a 2 over here. Then absolute value x plus 3 will be less than or equal to 7, I guess, right? The x itself will be less than 4. And when I add 3 to it, it will be less than 7, all right? But, and then when I begin the rest of the proof, I say something like, let delta be the minimum of 1 and epsilon over 7, right? That's where this 7 comes into play. But I'm here to tell you, this 7 right here does depend on the 3, right? I mean, it doesn't equal the 3, but if you change that 3 to something else, that will change the 7, right? It does depend on the 3. All right, one way that you can try and sort of visualize that dependence, you can see on a graph actually, this function, x squared, it's like that. Sorry, here's a little pro tip. When you miss the origin, you just put like a very fat dot right there. And then everybody thinks that you actually hit the origin. That's a little pro tip. I've been doing this for a long time. I know all the tricks. Check it out. What I just did was about 3. And if you kind of think about what the epsilon and delta proof means, here's f of 3, which is 9, right? This is not really to scale, but what the epsilon delta business means is if you choose some small window around here where this distance there is epsilon, it means that if you go over to the graph here, this corresponds to some window around 3, and this is the delta, right? That's the idea behind the epsilon and delta definition. What if instead of 3, you use some other number? How about, say, 10 over here, all right? Now, I'm going to miss the curve. 10 is too much. Can I go back? How about 7? I'm not trying to be super accurate here. 7 on the curve is up here. Look what happens though if so the value of 7 would be 49. Now if I use the same distance epsilon, I'm going to try to make this epsilon approximately the same width as that other epsilon I wrote. Check it out. What happens over here? The window around this point, in terms of the delta, is super narrow, much narrower than it was over there, right, around the 3. The window of values around here is super tight, all right? This is now the delta, okay? So in this particular example, higher values of C require smaller deltas. Using the same epsilon, a greater value of C will require a smaller epsilon in this case, right? And you could say the reason that happens in this example is basically because the slope is changing, right? all these little windows, I'm going to say vaguely this has to do with the slope. Although we're not really going to make too much of the relationship as of now, but this has to do with the slope. This is not always true, though. For example, so like this function here is not uniformly continuous when you consider its whole domain, because what uniformly continuous means is that you can use the same delta basically for around any point. Contrast that with something like a straight line. 2x plus 5. Looks like this. And this, if you try to draw those little epsilons and deltas, you'll notice actually you can use the same delta every time, the same width of the interval. It's because the slope is the same every time. So this one here, all values of c can use the same delta. In fact, in this particular example, I happen to know you can just let delta be epsilon over 2. Once you do all the simplifying, you factor the 2 out, and everything works out perfectly the way you want. This is like the very first examples we did of the epsilons and deltas. They all worked out in that way. Those were the easy ones. All right? So this is the basic idea behind uniformly continuous. Can you use the same deltas for every point, or do you have to change the deltas around as you go point to point? All right? So here's the real definition here. Let me just say, informally speaking, uniformly continuous means, I'll put this whole thing in quotes because this is not the real definition. This is just the idea. We can use the same delta for any point. You don't have to change the delta from one point to another. All right, here's the real definition. So I'm going to write that just in more formalistic language. But you will see, comparing this with the definition of pointwise continuity, they are very, very similar. Check it out. F is uniformly continuous on some set A, subset of R, and only if, I'm just going to write it and then we'll, for all epsilon greater than 0, there exists delta greater than 0, such that for any x and y in A, x minus y less than delta implies f of x minus f of y less than epsilon. All right, this is what it means to be uniformly continuous. It looks almost the same. I didn't use the letter C, so the definition of uniformly continuous, you could call it C if you want to, but I changed it to Y. This is meant to emphasize the fact that, so I use Y to emphasize that in this case now x and y play the same role. In the other examples where you have the x and the c, you somehow think about c as being like fixed in a specific location and the x is nearby the c, right? But I'm trying to think about not just any c, but some epsilons and deltas which work for every possible c. And so now it doesn't make any sense to try and specifically locate that point C. The whole point of this is that all this stuff works no matter what the C is. So we just consider x and y both to be points in A. The only difference, if you compare this to the pointwise definition, the only difference is that you see the y over here rather than in the middle. Remember what I said in the other definition began with that, right? At the beginning. Now, with uniformly continuous, that for all y has been moved past the epsilon and the delta. The effect of that is this y here, which is playing the role of c before. The effect is now epsilon and delta cannot depend on y. In the previous example, the previous definition, you put the c at the very beginning, And then after the C, you say there exists delta. That means the delta could possibly depend on what the C is. When you write it this way, though, so there's no for all y at the beginning. And you don't put it at the beginning, but you put it at the end. It means that you got to choose the delta before the x and the y are specified. In other words, the delta cannot depend on y. All right? This is a definition of uniformly continuous. Yes?
If delta and epsilon are supposed to be really small, what happens if your x and y are far apart?
Then this will be vacuous, because if x and y are far apart, then they will not be less than delta here. And so you have something like a false implies anything. And then it will,
okay.
you know what I mean, then it will automatically be true.
Okay.
So this, you know, like I always say, we never say that epsilon and delta are small, but the definition is only interesting if delta is small and if x and y are close together, right?
Okay.
Otherwise, it's not really saying anything. Yeah, that's a great question. All right, we got 8 minutes. Let's just do one specific example. Show that something is uniformly continuous. It's actually not difficult. You just have to use this definition, which is almost the same as the ordinary continuity definition. So let's show f of x equals 5x minus 10 is uniformly continuous on the set on all R. All right. What the set is actually makes a big difference when you're talking about uniform continuity. Although this is a simple example and it's not going to come into play. But in general, what the set you're talking about, the set A, is very important. But here it's not. But let's do it. So we're just going to do the usual structure here, right? We begin with epsilon. You know, it says for all epsilon there exists delta. So I'm just going to say let epsilon greater than 0 be given. And then we'll find delta. Oh, come on now. We'll find delta greater than 0 such that for all x, y, and r, x minus y less than delta implies, it's the usual thing, f of x minus f of y less than epsilon. All right. Now f of x in this case is 5x minus 10. So actually this I would ordinarily plug this in. I forgot to though. 5x minus 10 minus 5y minus 10. Don't forget the parentheses. All right. Can we do it? So as usual, you know, we're going to start with this thing, try to simplify and extract from it, in this case, x minus y. All right. So when you're doing uniform continuity, you will never have a specific constant in here. You know, most of our examples have been something like x minus 2. You could try to pull x minus 2 out. Uniform continuity, you don't get a specific value. So that can make it slightly trickier from time to time. It's not really a problem, though. So I go 5x minus 10 minus 5y minus 10. What can you do with that? Somebody shout it out. What is it? Yeah, cancel the 10s, and you end up with 5x minus 5y, right? Which is 5 times x minus y. And so I can let delta be epsilon over 5. Because I want 5 times x minus y less than epsilon by the 5. We've done this a million times before, right? So I say let delta equal epsilon over 5. Then if x minus y less than delta, we have, what do we get? I got to start with f of x minus f of y. So 5x minus 10 minus 5y minus 10. This is equal to 5 times absolute value x minus y, but that's less than 5 times delta, which is equal to 5 times epsilon over 5, which is epsilon. That's it. All right? This is a pretty standard epsilon and delta argument. And it works. This is uniformly continuous, really because this is the equation of a straight line, right? If you have something that's not a straight line, you do not expect it to be uniformly continuous on all of R, okay? We got 4 minutes. Can I just say one more thing in the remaining 4 minutes? I wanted to do another definition showing that something or other is not uniformly continuous. So how do we show something is not uniformly continuous? Are there questions about that? I should have asked before I scrolled along. This is pretty standard, very similar to other things we've done so far. So to show something is not uniformly continuous, we use sequences as always. Only it gets a little more complicated here, because for ordinary continuity, we find, let me just refresh your memory, f is not continuous at C means there exists a sequence xn converges to C, but f of xn does not converge to f of C, right? This is how you show something is not continuous at a point. How do you show something is not uniformly continuous? Basically, I need to replace the C with any point y. But the fact that both x and y can vary in the definition of continuity, which means really we're talking about two sequences here. So I'm going to put in blue, this is still not my final answer, but f is not uniformly continuous on the set A if basically you have two sequences, xn and yn with the same limit. See, before we had xn approaching C, but I want to allow the C also to vary, but they still have to approach each other. So I'm going to say that xn and yn are two sequences with the same limit, but f of xn and f of yn do not have the same limit. All right. I said that in parentheses. This is the basic idea. The official sort of the more convenient way to write this what I wrote is true, but it's a little more convenient to write it. I'll write this as a theorem. We're not going to do the proof here. Switch to black. This is the real deal. F is not uniformly continuous on A if and only if there exist two sequences, xn and yn, both sequences in A. I didn't specify that in the blue zone, but that's what I meant. Two sequences in A with, I want to say they have the same limit. The cuter way, or the easier way to say that, and this ends up being easier to handle when you go to actually prove things with it, is this. Rather than saying they approach the same limit, you can just say when you look at their difference, it goes to 0. That's the same as saying they basically go to the same point. But, or but, I'll say but, the f of xn and the f of yn do not approach the same limit. So I'm going to do that in the same way by subtracting them. F of xn minus f of yn does not converge to 0. All right? And it turns out this is fairly easy to verify in particular examples. And we'll start off next time with that, since we're out of time. All right. See you all on Friday.